Hello, and welcome to this video on the Certificate Rotator for AWS IoT Greengrass. The Certificate Rotator is a Greengrass component that is listed in the Community Catalog on GitHub. It is an end-to-end reference implementation of a device certificate and private key rotation process. My name is Greg Breen, and I'm an IoT Specialist Solutions Architect with AWS. We're going to dive deep into the Certificate Rotator. I'll start by explaining in more detail what it is and the value it offers. I'll cover the design goals and the system architecture. I'll walk you through deploying the solution, and I'll demonstrate certificate rotation for a fleet of Greengrass core devices. I'll cover how to configure the solution with different key and certificate options, and I'll perform additional certificate rotations using those options. And finally, I'll go into the details of how you can develop and test the solution should you wish to modify or extend it. The Certificate Rotator is delivered with extensive unit and integration tests and a CI/CD pipeline. So let's give a better definition of what this thing is. The Greengrass Certificate Rotator is a solution consisting of a Greengrass component and a companion cloud backend. The backend is delivered as a Cloud Development Kit or CDK application. Per the guidance given in the IoT lens of the AWS well-architected framework, certificate lifecycle management, including certificate rotation, is a security best practice. Although certificates are typically long-lived credentials, customers should, depending on the security posture of their workload, have the ability to rotate certificates ahead of expiry or in response to compromise. Implementation of certificate rotation is, however, undifferentiated heavy lifting for customers, and this solution eases that burden. This solution delivers a mechanism to rotate certificates without dictating when or why it should be done. Customers can use the Certificate Rotator solution to suit their own security needs and help improve their security posture. And finally, although the Certificate Rotator can be deployed as is, it's also an extensible reference implementation delivered as open source so that customers can tailor it to suit their needs. Let's now cover the major design goals and the high-level architecture. A major design goal is to support rotation of the private key in addition to the device certificate. This allows recovery in the unlikely event of key compromise and also gives customers a pathway to change the key algorithm to more secure algorithms in future. Greengrass supports storing the certificate and private key in either the device file system or in a PKCS11 hardware security module. This solution supports either storage option. AWS IoT Core allows customers to issue device certificates without public key infrastructure and without their own certificate authority. However, customers often want to use their own certificate authority. One reason being to control the expiry date of device certificates. This solution supports either AWS IoT or AWS Private Certificate Authority as the certificate issuer. The Greengrass Edge runtime can run on either Linux or Windows. This solution supports both of these operating systems. AWS IoT jobs encapsulate the certificate rotation process. Customers can use the powerful feature set of jobs to manage certificate rotation at scale across their fleet. Since a certificate rotation is triggered by creating a job, customers have flexibility in defining the rotation trigger to suit their own business needs. The solution is designed to be resilient to perturbations such as power loss, device reboot, or Greengrass service restart. And finally, the solution supports all of the certificate signing request signing algorithms supported by AWS IoT Core. Okay, let's now look at the architecture of the solution. The solution is principally comprised of a Greengrass component, 3 AWS IoT Core rules, 3 Lambda functions, a custom AWS IoT job template, and a simple notification service topic. Certificates are issued by either AWS IoT Core or by AWS Private CA. The cloud application initiates a certificate and private key rotation by creating an AWS IoT custom job using the custom job template. The Certificate Rotator component is notified of a new certificate rotation job. The component updates the job execution status to in progress. The cloud then notifies the component that the job execution update is accepted. The Certificate Rotator component generates a new private key and creates a certificate signing request from it. The component sends the CSR to the cloud backend along with the job ID so that strict chain of custody can be maintained. The Create Certificate Lambda validates the creation request and creates the new certificate using either AWS IoT or AWS Private CA. It attaches IoT policies to the new certificate and attaches the new certificate to the thing. The cloud backend returns the new certificate to the Certificate Rotator component. The component backs up the old certificate, installs the new certificate on disk or in the HSM, and restarts the Greengrass service so that it will attempt to connect using the new certificate and private key. After the restart, the component gets the latest job context. If the new certificate and private key are good, the job execution status is returned by the cloud and the status is in progress. The component asks the cloud backend to commit to the new certificate. The request includes the job ID so that strict chain of custody can be maintained. The commit certificate lambda validates the request and verifies that the principal used to make the MQTT connection is the new certificate. The cloud backend then notifies the component that the new certificate is good and that it can be committed. The component deletes the old certificate and the old private key. The component then updates the job execution status to succeeded. The job execution terminal lambda deletes the old certificate from the AWS IoT Core registry. The cloud notifies the component that the job is completed. If any errors occur, the job execution will terminate with state failed or timed out, causing the job execution terminal lambda to issue a notification on the SNS topic. If an error occurs after the new certificate and private key are installed on Greengrass, a rollback will occur. Okay, that's been a lot of talking. Let's get on with the business of deploying the solution. To deploy, we first need to set up one or more Greengrass core devices in a fleet. Then we need to satisfy some prerequisite requirements, and then deploy the cloud backend and the Greengrass component. If you already have Greengrass core devices, then you're good to go. If not, I've used the Greengrass EC2 device farm to create a fleet of devices as EC2 instances. A link is in the video description. The device farm creates a fleet of 8 core devices with disparate operating systems and processor architectures. It creates a thing group containing all of the devices, and it creates a deployment targeting the Greengrass EC2 device farm thing group. Okay, we jump now to the Certificate Rotator repository. A link is in the video description. The repository documents the prerequisites, and we're going to follow those instructions. We start with the core device requirements. The EC2 device farm devices already satisfy the platform requirements and the Python requirements. The device farm devices are EC2 instances and don't include an HSM, so the HSM requirements don't apply. The Edge runtime is already installed, and it's installed as a system service. We need to change the Greengrass nucleus configuration to some non-default values. We'll use AWS Private CA for a part of this video, so we need to change the Greengrass data plane endpoint to IoT data. And the Certificate Rotator component uses recipe interpolation, so we need to enable that feature. So what is interpolation? Looking here at the component recipe, we can see the access control configuration. The component uses a thing name variable to create least privileged topic definitions. Interpolation replaces this variable. Okay, so let's deploy the configuration change. We revise the device farm deployment. Explicitly add the nucleus to the deployment so that we can modify its configuration. We select the nucleus for configuration, add the two variables that we need, and then deploy. Okay, so we move on now to the cloud prerequisites. The Greengrass component artifacts will be stored in a bucket defined by the GDK config JSON file. I won't change the default name. The core device role or token exchange role needs to be given access to this bucket. So in my case, I've modified the device farm token exchange role to allow access to this bucket. The IoT policy for the Greengrass core devices must allow the devices to publish and subscribe to the topics that we saw in the recipe earlier in this video. In the case of the device farm, it has a permissive policy because it's only intended for non-production environments. If you deploy in production, your policy should grant least privilege. On your machine, you need to install the AWS CLI, AWS CDK, Python, pip, some Python packages, and the Greengrass development kit. On my machine, I already have the tools installed, so I now clone the repository. Once done, I change into the directory and create a Python virtual environment, activating it, and now I can install the Python packages. And finally, the Greengrass development kit. All deployment prerequisites are now in place. Now we can build and deploy the cloud backend. These are the steps we need to follow. So I firstly change into the backend directory, then install dependencies for this CDK application. We can then build the application and then deploy using CDK. Since we haven't modified the CDK context at all, this deploys the backend with default settings. AWS IoT is the default CA and certificate issuer. Looking in the console, we can see the resources that were created. Here we can see the CloudFormation stack, the 3 AWS IoT core rules, the 3 Lambda functions, the SNS topic, and the custom job template. It's time to build, publish, and deploy the Greengrass component. These are the steps we need to follow. The GDK config JSON file has several configuration parameters, including the AWS region that the component should be published to. This defaults to US East 1. If you want to publish to a different region, please edit this file. In my case, I'm using the default region. I can now build the component using GDK and publish it to my account. GDK will create the Artifacts S3 bucket if it doesn't already exist. This is the bucket name we previously added to the token exchange role. Looking in the console, we can see the published component. Let's deploy it. We start by revising the existing deployment. We need to add the Certificate Rotator component to the deployment. Engage now in a little bit of ClickOps, and then deploy. The component installs some packages when deployed, so after a short delay, the deployment succeeds on each device. Let's look into the component log on one device. After installation, the component starts up. It gets its configuration. These are the default values. We'll discuss these later in the video. It subscribes to all of the necessary topics. It then asks IoT Core if there's any certificate rotation job available. In this case, there's not, so the component enters an idle state. With deployment completed, we can start rotating certificates. As a last step before performing a certificate rotation, let's check an existing certificate. This is the Ubuntu 22.04 x86 device in the device farm. It currently has certificate ID 9E65 attached. Drilling into the certificate, we can see it was issued by AWS IoT. It was created April 21st at 8:25 and expires at the end of 2049 in UTC time. Please bear these details in mind for when we check the device after the rotation. Okay, this is it. We're really going to perform a certificate rotation now. So we create a job, more specifically a custom job. We give it a name, select the target group or the target things, in my case the device farm, and then we create the job from a template, in particular the certificate rotation template. A snapshot job will usually be the right choice for a certificate rotation. Note that here you can also modify various job configuration options to suit your needs, taking advantage of the power of IoT jobs. Once done, we submit. Once created, let's view it. Certificate rotation takes in the order of 1 minute. In general, the Linux devices finish considerably quicker than the Windows devices. And after a short delay, there you have it. All job executions have succeeded. Returning to the Ubuntu 22.04 x86 device, we can see that the certificate ID has changed. Drilling in, the new certificate has the same issuer and the same expiry date as expected. However, the creation time is new, confirming that it's a new certificate. Looking on one of the devices, we can see the last modified time of both the private key and the device certificate, confirming that both of them were changed by the rotation. Inspecting the component log, we find records of the job notification, the device changing the job status to in progress, the private key and CSR creation, the certificate creation request, the certificate being sent to the device, and the device restart. Scrolling down, we find the device requesting the job context, requesting a commit, committing to the new certificate, and updating the job execution status to success. Let's look at the configuration options for the Greengrass component. The Certificate Rotator component has two configuration parameters. The key algorithm defines the algorithm that the component will use for any new private key it generates when a rotation is performed. 4 algorithms are supported, with RSA 2048 being the default. The signing algorithm defines the algorithm that the component uses to sign the CSR during a rotation. The component supports all 6 algorithms that are supported by the AWS IoT Create Certificate from CSR API operation. The family of the signing algorithm needs to be the same as the family of the private key. In other words, you can't have an RSA private key and an elliptic curve signing algorithm, or vice versa. The component validates configuration changes before applying them. If there's an attempt to merge invalid configuration, the deployment fails. Okay, so let's change the component configuration. For the sake of brevity, I've already modified the configuration, setting the key algorithm to RSA3072 and deployed it to the device farm. Inspecting the component log on a single device, we can see that the new configuration was validated and accepted. Before we rotate with this configuration, let's inspect the existing private key. It uses RSA2048 as expected. Likewise, let's check the existing certificate. And as expected, the public key is also RSA2048. So let's rotate certificates again, this time using the CLI to create the job. And after approximately 1 minute, the job is completed, with the rotation successful on all 8 devices. Inspecting the new private key on a device, we can see that it's an RSA3072 key. Likewise, checking the new certificate, it has an RSA3072 public key. Let's cover how to configure the cloud backend. The cloud backend is configured using 3 CDK context variables. You only need to concern yourself with these if you wish to use AWS Private CA to issue certificates. The PCA CA ID variable specifies the ID of the private CA to use. By default, it's an empty string, which selects AWS IoT as the certificate issuer. If you enable AWS Private CA, the validity in days variable specifies how long a newly issued device certificate is valid for, and hence you can control the expiry date. The signing algorithm variable selects the certificate signing algorithm. Switching to AWS Private CA, you can see I've created a short-lived CA, meaning the maximum validity of certificates is 7 days. It's an elliptic curve CA, and I've highlighted the CA ID that we'll use in the next step. The CA is owned by any company, so we should see that as the issuer in new device certificates. So let's redeploy the cloud backend, passing the CA ID and selecting SHA-512 with ECDSA as the signing algorithm. Okay, let's create another certificate rotation job using the CLI. And after a minute, the job is completed successfully on all 8 devices again. Once again, we inspect the new certificate on a device and see that the public key is still RSA3072 because the new private key still uses that algorithm. As expected, the certificate issuer is any company. The certificate is valid for only 7 days, and the certificate signing algorithm is ECDSA with SHA-512. We'll finish by examining the code quality measures used for development and testing. The component and Lambda functions are developed in Python, with the expectation being that this appeals to a wide audience. Accordingly, the tooling is Python. PyLint is used for static analysis, PyTest for unit testing, and Bandit for security scanning. Let's see these in action. Firstly, PyLint. 10 out of 10. Always a good feeling. Now, Bandit. 0 issues found. And PyTest. 154 test cases passing. This command produces an HTML coverage report. And that report shows 100% line and branch coverage. This solution includes integration tests that use Robot Framework as the test harness and your machine as the test runner. Test cases make API calls to the cloud to create Greengrass deployments and certificate rotation jobs, with these deployments and jobs targeting a test fleet of real Greengrass devices. These may even be physical devices on the lab bench. Scrolling down, Robot Framework is a Python package that needs to be installed. To execute the integration test, the caller must supply two Robot Framework variables: the name of the thing group containing the Greengrass core devices that are under test, and the ID of the AWS private CA to use for test cases that test issuance of certificates using AWS private CA. So let's run them. We change into the robot directory, install the Python packages, and then run the test suite, passing the device farm thing group and the AWS private CA ID we discussed earlier. 40 minutes later, and all tests have completed successfully. There are 4 test suites. The first checks that invalid component configuration is rejected. The second validates certificate rotation with AWS private CA as the issuer. The third validates certificate rotation with AWS IoT as the issuer, checking all component key and CSR signing algorithm combinations. And the fourth validates rollback and recovery for error conditions. Note also that Robot generates a detailed log file. Inspecting the log, we can see the duration was 4344. And note that in this log, it's possible to drill down to great detail. The solution includes a CI/CD pipeline that's intended for non-production environments. The pipeline consists of 2 stages: one AWS code build stage to build and deploy both the component and the cloud backend, and another stage to run the integration tests. The build and deploy stage runs the static analysis, unit tests, and security scanning that we already discussed. It uses CDK to deploy the cloud backend and uses AWS IoT Core and the Greengrass cloud services to publish and deploy the component to a test fleet of Greengrass core devices. The test stage runs the same integration tests that we covered just moments ago. The pipeline has 6 CDK context variables. Connection ID is the ID of the AWS CodeStar connection to the forked repository, and owner name is the name of the owner of that forked repository. Repository name and branch name are self-explanatory. Thing group name and PCA CA ID are the 2 variables needed by the integration tests, as we covered earlier. As they don't have default values, you must set them for deployment. So let's deploy. I change into the directory, install dependencies, build the project, and deploy it using CDK. I've already forked the GitHub repository to my personal account and created a CodeStar connection to it. The pipeline runs when freshly deployed, and after 40 minutes, it completes successfully. Thank you for watching this video. If you have any questions, please ask them at repost.aws.